Hello, everybody. My name is Ahmed Mahmoud. I'm a PhD candidate at University of California, Davis, senior research scientist at Autodesk Research. In this talk, I'm pleased to share our work on GPU mesh data structures that we developed to speed up geometry processing application on the GPU. In this work, we focus on triangle meshes because they are everywhere and are used in so many applications, from simulation, modeling to visualization, and so many computational geometry applications. One of the reasons for the popularity of triangle meshes is the existence of well-developed, mature libraries that make working and managing meshes with thousands and maybe millions of triangle faces very easy. Example of this library include SIGGRAPH, OpenMesh, and libIGL. However, most, if not all, of this library perform mesh processing on the CPU, and it is not easy to extend such an existing CPU-based library to work efficiently on the GPU. So the question we ask is that how to leverage the GPU massive parallelism for mesh processing. And our solution is twofold. The first part is a programming model that is intuitive and to provide a high-level abstraction for a large set of geometry processing application. And second is a data structure that can perform a query operation with a high performance on the GPU while being generic and compact. We will start first discussing our programming model, and then we will move to discuss the data structure. Generally speaking, GPU-specific programming models have a huge success for many domains, including sparse voxel computation, simulation, image processing, and graph processing. And the reason for this success is that they free the user from thinking and or optimizing the low-level implementation details, and they make it easy for the user to find solution more robustly, quickly, and with high performance. And this has motivated us to create a programming model for surface triangle mesh. Our programming model is focused on applications that require local computation. By that, I mean the application where the information the user needs is related to the mesh local neighborhood. A simple example of this application includes computing discrete geometric quantity like the Laplacian or phase normal. And our programming model is quite simple. However, we believe it's powerful enough to implement a diverse set of applications. Using our programming model, the user only think of the local operation applied to a single mesh element. This operation may involve a query operation to adjacent or and incident mesh element, or query the mesh attribute like the vertex coordinate or face normal. The programming model is inspired by a thing like a vertex programming model used for general graph processing, where the user develops their algorithm by focusing on one vertex and the computation on the vertex based on its local data and its neighbor vertices and edges. We extended to all mesh elements that we might operate on, namely vertices, edges, and faces. As the implementation of the programming model is then responsible of assigning mesh element to GPU threads with the goal of exploiting locality, induced load balance, which is very important for high performance. We can show how to use this programming model on a very simple example of computing vertex normal, which can be done by first computing the normal of each face, shown here in different colors, and then adding them up to the vertex. Of course, this is just one way of computing the vertex normal. We can do this in parallel by thinking of what type of computation the face should do. So every face in parallel should first query its three vertices, compute its normal using the coordinate of these vertices, and finally add the normal atomically to the three vertices. And this is how the user code would look like in our programming model. The query operation is defined as a simple temporal parameter. Operation applied to the query or output are defined in lambda function, which has an iterator and edge signature, from which the user retrieves the faces vertices. The normal computation can then take these three vertices along with the coordinate buffer, and then finally the normal is atomically added to the three vertices. So under our programming model, the user responsibility is just to composing their computation by defining what computation a single mesh element should perform. The implementation of the programming model then takes this computation and run it in parallel for all mesh elements in such a way that maximizes locality, induces load balance, and eventually leading to a higher throughput. And what enables us to do this is the data structure, which we will move now to discuss its design goal and the design principles. First, this is a list of all the query operations that our data structure can perform. We call this operation the first order query, since they query the immediate neighborhood of a mesh element. Our data structure also perform a higher order query, such as querying the Turing of a vertex. All these query operations are the same operations that one can perform using a half-edged data structure. We will start off by specifying the design goal of our data structure. These are the things that we would like to achieve at the end. First and foremost is achieving high performance by efficient utilization of different layers of the GPU memory hierarchy. This can only be achieved if we are able to improve the locality of the query operation. And one way to do this is by confining the computation within the GPU shared memory. Second is generality. We make no assumption on the input mesh quality. It could be non-manifold, non-orientable, or containing self-intersection. We assume also that the user requires operating in all mesh elements. These are the vertices, edges, and faces as dictated by the programming model. The third is compactness. While it is possible to pre-compute all query beforehand, this will needlessly increase the global memory footprint. More importantly, since the GPU shared memory has a limited capacity, increasing the memory might limit the amount of locality we can exploit. So we strive to store a minimal amount of information and instead efficiently compute the query dynamically. Now we move to discuss the design decision and the principle we have taken in building our data structure. The traditional method to capture locality and thus increasing the memory throughput within the context of mesh processing is through global sorting, which means that we sort all mesh elements in some coherent way, as shown here, and we rely on the L1 cache to do its job, which works very well on the CPU since it has a relatively larger caches. Using this approach on the GPU and due to the limited L1 cache capacity, we have observed that the L1 cache got exhausted very rapidly, since we rely on it to cache both the mesh connectivity information as well as the mesh attributes. For this, we opt to a different approach in order to capture locality, which is batching. With batching, we subdivide the input mesh into small batches that can fit into shared memory and perform all query operation inside the shared memory. This guarantees that we always are able to exploit the highest memory bandwidth, even if the mesh attributes are used during computation, which is always the case. Now that we have the batches, we turn into discussing how to store them. We, of course, are looking for a representation that is compact, such that it can fit in the shared memory, and allowing high concurrency. But since batches are small, we can use reduced precision to represent mesh element, and for this, we use 16-bit indices. Second, we use the linear algebraic representation to represent each batch independently. The linear algebraic representation can be used to represent any simplicial complex. However, we specialize it and optimize it for triangle mesh, which requires storing only two very sparse matrices. We believe that the linear algebraic representation is a good fit for representing batches since it's optimized for space. In other words, it stores minimal amount of information and rely on dynamically computing the query on the fly. So the first metric in the linear algebraic representation for triangle mesh includes the connectivity from edges to vertices, and the second matrix includes the connectivity from faces to edges. Using only these two matrices, we can perform all different query operation we have listed earlier via sparse matrix multiplication or matrix transpose. We do different optimization to make this operation as efficient as possible, from how we store these sparse matrices and how we compute the matrix multiplication or matrix transpose on the fly inside the shared memory. And the paper discusses implementation details. However, one of these optimization is how we map work to threads. The traditional method of assigning CUDA threads is to assign one thread to a mesh element. For example, one thread per vertex, and each thread work in isolation. Problem with this approach is that it leads to load imbalance, branch divergence, and the memory divergence, as one thread would be doing more work since it may be assigned to a vertex with higher valence than the other threads in the same org. This would be the case if we have chosen to represent batches using half-edged data structure. But since batches are represented using the linear algebraic representation and perform a query as a matrix operation, this enables us to map work such that threads within a CUDA block can work collaboratively to perform their work. This ensures good computation performance through load balance. The paper discusses how we do this in more details. But what I want to highlight here is that this work mapping strategy is not exposed to the user at all. The user gets the impression that one thread is assigned to a single mesh element and work independently, which is a very simple mental model when one thinks about computation. But under the hood, the query are performed more efficiently. So far, we have been focusing on independent batches. Now we move to discuss how these batches are placed in a more global context where we can do some useful work. One problem we can see directly is that a mesh element on the boundary of the batch would require a special treatment because it needs to read a neighbor batch information. If we did this, we would lose the benefit of locality, and they might also lead to load imbalance. For this, we augment each batch with the ribbon shown here in white, which is the union of the one ring of the batch's boundary vertices. And this become part of the batch information. This will lead to a moderate increase in memory usage per batch, while significantly increase the locality. This increase in memory is justified since we have picked a very compact representation for the batches. The other challenge is that the user expects a single index per mesh element. And so far, in order to identify a mesh element in a global context, we have to use the batch index in which the mesh element resides, along with its local index within the batch, which is quite inconvenient. For that, we create another index space for all mesh element called the global index space. And this is the index space that the user interacts with, and they can be used to index the mesh attributes, for example. So in other words, the local index space is used to perform a query within the batch, which has the benefit of locality. Then the output of the query operation is mapped to global index space, which the user can use as if everything took place in this global index space. Now we will move to evaluate the performance of our data structure and the programming model. In our evaluation, we assess the performance of the data structure first on the low-level query operation that we have listed earlier. And we do this in order to have a fine-grained understanding of the data structure performance. Second, we also assess the performance within a full application, which is what the user cares about at the end. We have picked 3 data structures for comparison, two that run on the CPU, which are OpenMesh and SIGGRAPH, and they are based on half-edge data structure. And the other is the GPU parallel version of directed edges. Directed edges is an optimized version of a half-edge data structure for triangle mesh, where we are able to include some information implicitly, which help reducing the memory transaction. In general, OpenMesh and SIGGRAPH have the slowest performance in all cases by an order of magnitude, and this huge performance gap motivates even further the development of a general-purpose data structure and libraries that leverages the GPU. Moving forward, we will only focus on comparison against BDE. In the query operation evaluation, we test against different input variants defined by the input order. The first one is a default input order in which the mesh element index is assigned as defined in the input file. The locality accepted in this variant is not consistent and highly dependent on how the mesh is being generated. To gain a better understanding, we experiment with 2 other extreme cases. The first one is we sort the mesh element indices in such a way that locality is maximized. And thus, we expect caching to be more effective with this input order, and thus higher performance. The other extreme case that we experiment with is to randomly shuffle the mesh element indices, something that we might encounter when working with meshes in the wild. And this is a summary of the speedup RXMesh against BDE. The paper has more in-depth analysis of the performance of BDE and RXMesh, but there are a couple of interesting points that we would like to highlight here. First is that with the sorted variant, where we expect BDE to perform the best, RXMesh is still able to outperform on some of these query by being on average 3 times faster. This proves that batching and using shared memory is a more effective way to capture locality and improve performance than sorting, where we rely just on the L1 cache. For the query operation on the last 2 columns, directed edges is faster by a maximum of 1.6 times than RXMesh. And this behavior is consistent regardless to the input order. This is because BDE is well optimized for these 2 operations. It actually doesn't perform any computation for these 2 queries, where every thread just writes 2 4-byte numbers to the global memory, and it only works for manifold meshes. Having RXMesh just slightly slower than BDE for this operation, while being generic in terms of handling non-manifold meshes, and outperform on all other operations is a trade-off that we have chosen. Now we move to the application evaluation. We picked 4 geometry processing applications and compared against BDE using the sorted input order to maximize its performance. The important part I want to highlight here is that each application explores and tests a certain aspect of our data structure and the programming model. For example, mesh smoothing using mean curvature flow implements the conjugate gradient solver in a matrix-free fashion, and thus this application shows the performance of repeatedly querying the vertex wandering within an application. And we found that RXMesh is on average a 4 times faster. There are so many applications that have the same computational pattern, like mesh parameterization and surface modeling using as possible technique. And thus we believe RXMesh would be a good fit for this application. The next application is geodesic distance based on the front propagation for computing approximate geodesic distance using recent algorithms that work in parallel on the GPU developed by Romero and the colleagues. The application proceeds in multiple iterations, starting with the wandering of the source to vertex and propagate information from one topological level set to the next one. In every iteration, only the vertices in the topological level set are processed. Using BDE on sorted input, it is often the case that how the vertices are sorted doesn't align well with the propagation direction, and thus we find many cache messes when processing a topological level set. Using RXMesh and thanks to batching, the locality is maximized. Since we read the batch only once into the shared memory, and once it is read, we have all the information, even if we are processing only a subset of the vertices as defined by the topological level set. And this explains the performance boost we get with RXMesh, which are around 15 times faster than BDE. Third application is bilateral filtering, which essentially filter out the high frequency noise from an input mesh, which is similar to the mean curvature flow application. However, the intent of this application is to assess the performance of RXMesh to generate higher order query, which are queries that goes beyond the immediate neighbor. The critical part of this application works by placing a ball around each vertex and collect the vertices that happen to fall inside this ball. This happens by progressively query the key ring of the vertex, starting with k equal 1. At each step, we check if any of these key ring vertices fall inside the ball. If none fall inside the ball, then this indicates that we have already collected all the vertices that fall inside the ball. In this application, RXMesh actually has a similar performance as BDE. And the reason for this is that using RXMesh, we have to read additional batches that goes beyond the one ring, which increase the total global memory transaction. We have planned to improve the computation further by efficient scheduling of the computation. Our final application is a vertex normal that we have showed earlier. While being very simple application, it provides us with the insight of how RXMesh perform against the higher hardwired application-specific data structure, which should always give us the optimal performance. For this application, we only query the phase 3 vertices, and thus we use the index triangle for this comparison. And we find that index triangle is only just slightly faster than RXMesh, and this is really encouraging because it means that RXMesh generality virtually imposes no performance penalty. For future work, our next target is dynamic changes. Of course, static meshes on the GPU has broad applicability, but supporting dynamic changes will enlarge the set of applications we can support. The fact that we use batches to capture locality makes it possible to parallelize dynamic changes across batches with higher concurrency. However, the biggest challenge is the semantics. In other words, what is the right thing to do when one thread tries to change a vertex that is being deleted by another thread? And it is such an interesting research direction to explore different semantics that can be realized in a programming model that is simple and offer a higher abstraction for a larger set of applications. And this is what we are working on right now. Another direction that we hinted to earlier is improving the higher order query. Quad meshes sounds like a natural extension. However, volumetric meshes are a bit of a challenge because we will need to store more information per batch. Since now we are dealing with vertices, faces, edges, and volumetric elements, which will put more stress on the shared memory and thus less occupancy. In conclusion, we showed that capturing locality is important to improve performance on the GPU. Relying on the hardware caches has been the standard way to do this, but we showed that the programmer manage caches using the shared memory is more effective, and they can improve performance even further. And it is possible to hide this complexity from the user beneath a very simple programming model. At the end, I would like to thank my collaborators at UC Davis and Autodesk, and for our funding agency. Our code is available and they can be accessed by following this link or scanning the QR code. Thank you for listening.